Hi class, today we are going to study about the AC circuits, AC circuit networks, starting with the circuit law theorem. If you remember, we had the circuit theorem single phase series. Actually, we use the circuit laws and theorems. Those circuit laws is that you are lucky we use to do with the DC circuits, remember. So here Ohm's law will be applied. The circuit also will have the single phase series and the parallel circuits, single phase series and parallel circuits. Also we have the three-phase system, and also the part of complex application of complex number in the AC circuits. So you can see that the DC circuit is slightly not complicated like as it is in the AC circuit. First, today we are going to see the resistor color coding and ohmic values. This is a color coding, like I can see here, the silver color. When you look at color coding, let us see here. It's like this one. You find the resistor with those color coding, and therefore those color coding say that if the color is silver, it's high number, it doesn't have a significant figure. There's no silver in the first, but if the gold is 10 power minus 1 multiplier or tolerance, if it's black, it is 0. If it is brown, if it's red, orange, yellow, green, blue, the white has got those values as you can see here. Now, for instance, if there's 4-band fixed resistor value with two significant figures, yellow, violet, orange, red, indicates that it is 47 kilo ohm with a tolerance of plus or minus 2%. Here you can see the last one is red. Okay, you can see red is say that it's a tolerance of plus or minus 2%. You can see. Then he say red, orange is 10 power 3. Okay, and the first one is yellow, violet. Yellow is 4 and violet is 7. So you get the 4.7 kilo ohm. So orange, if it's orange, silver, brown, orange is what? We already say it's 7, I think. Orange is 3, 10 is 3. First orange is 3, and the orange again is multiplied by 10 power 3. So it's orange, silver, brown is 0.33 ohm with the tolerance of plus or minus 1 because it is silver plus 1. So brown is tolerance of plus 1, and orange, say orange, silver, brown. Orange, silver, brown. So this is how it is working. So this is an example. You may look others as we go. Letter and the digit code for resistance, like 0.47 ohm, marked R47, that is 0.74 ohm. 1 ohm is 1 R0, 4.7 ohm is 4 R7, 47 ohm is 47 R, 100 ohm is 100 R, 1 kilo ohm is 1 KO, 10 K ohm is 10 K, etc. So this is also another coding you might find it. Another one you can see here is the resistor color code. As here they said black is 0, brown. This is the table you can read and find these values rather than be lectured. But what I mean is that first strip, second, third, and fourth have the meaning. First is digital, multiplier, and tolerance. So here, for instance, we have first is digital, second is digital, third is multiplier, and the fourth one is torrent. So here, digital, like first and second is digit. So if it is brown, it's 1, orange 3, then multiplied by 1000, and tolerance. That is how it is looked. Like here, for instance, here you have gold, black, gold. Say first is red, second is red, third is black, tolerance, fourth is gold. So we can go to the chart and see. Red is 2, 2, and red, I mean, no, not this one. This one. Red, multiply black. Black is how much? Black is 1, and the gold is partial 5. So this will give you how much? Black color is order of plus 5. So it's 2, 2, 1 plus. So it's 22 ohm plus or minus 0.5. That's how they do it. So this is the simple. You might follow them as we go. Resistance color code example. Determine the resistance of the given resistor with the given color sequence: red, green, red, gold. As we know, the first two colors represent the significant digit of the resistance value. So we give color representing 2, red is 2, green is 5. Is it? Red is 2, green is 5, so 2, 5. And then what next? Red is multiplier. How much is this? Red is multiplier 100, and the gold is tolerance. Tolerance is 5%. So you can see here. 5, the third band is multiplier band, hence the color red represents the multiplier factor by 100. Last band represents tolerance level, and their level is plus or minus, hence it would be 225 kilo ohm. 2500 plus or minus 5%. So that would be 2.5 kilo ohm resistance. Until now, we have discussed DC. As I say, supply a DC circuit, but 90% of the electrical energy used nowadays is AC. You remember, almost all big machines in the industry, they use the AC circuit in nature. Electrical circuit supply used for commercial purpose is alternating current. The DC supply has constant magnitude with respect to time. As you can see in the figure 6.1, show the graph of current with respect to time. Such change in magnitude and direction is measured in terms of cycles. Each cycle AC consists of 2 half, positive cycle and negative cycle. Current increase in magnitude in one particular direction attains maximum and start decreasing, passing from 0. It decreases to opposite direction and behave similar. So the fig 6.1 shows the graph of alternating current. You can see such change in magnitude and direction is measured in terms of cycles. Each cycles of AC consists of 2 half cycles, namely positive and negative cycles. Current increasing in magnitude in non-particular direction, attain maximum and start decreasing, passing through 0, decreases in opposite direction and behave similar, as you can see in figure 6.2. If you want to invert your AC circuit. Now, in practice, some waveforms are available in which magnitude change but direction remain the same as positive or negative. This shows in figure C. Wave is known as a pulsating DC. The waveform obtained as output of full wave rectifier is an example of pulsating DC. So this is an introduction that we have AC and DC, and AC behave as a cycle, maximum positive and maximum negative, then goes to zero again. But for the case of DC, they are always constant. So electric laws and theorems, as we say that in AC circuits, we'll have Ohm's law, which says that the current flowing in the circuit is direct proportion to the applied voltage and inverse proportion to the resistance, provided the temperature remains constant. This one you know from the DC side. Also, we have the laws of electromagnetic induction. These laws of electromagnetic induction state that an induced EMF is set up whenever the magnetic field linking with that circuit changes. When there's a change in magnetic flux linkage, this is where we can get this transformer, how the transformer magnetic flux changes, then the EMF is induced in that circuit. The magnitude of the induced EMF in any circuit is proportional to the rate of change of the magnetic flux linking the circuit. Lenz's law, the direction of induced EMF is always such that it tends to set up a current opposing the motion or change the flux responsible for inducing that EMF. Another law is the Lenz's law. Direction of induced EMF is show the direction of. So the direction of an induced EMF is always such that it tends to set up a current opposing the motion or change the flux responsible for inducing that EMF. This is the Lenz's law. The maximum power transfer theorem that states that the maximum power transfer from supply source to a load is at its maximum when the resistance of the load is equal to the internal resistance of the source. That means when the internal resistance is equal to the maximum load, to the load, that's the maximum power it can transmit. Also, see the direction of the magnetic lines of the flux is given by the screw rule. The screw rule you consider as you have a screw drive, or you drive your screw. So the direction of the screw drive is always clockwise. You put clockwise, the direction of the screw is forward. So if a normal right-hand thread is screwed along this conductor in the direction of the current, the direction of the rotation of the screw is the direction of the magnetic flux. AC circuit theorems, analysis. The objective to demonstrate the understanding of the superposition theorem, Thevenin theorem, Norton theorem, and maximum power transfer theorem as applied to AC circuit. To demonstrate the understanding of impedance matching transformers, demonstrate the understanding of the bridge circuit analysis. This is a part of the research they did, but according to this lecture, we are not going to cover all of this. We shall examine the number of theorem and technique to help us analyze complex circuit and address specialized application. We begin to examine the concept of the source independence in zero to make more accurate models in our idealized constant voltage and current sources. This will be step beyond using the simple resistance as found in the DC cases. We have a slightly complicated circuit using this AC circuit. From there, we will investigate how to convert from one type of source to another, such as creating voltage source that is functional equivalent of current source. The function equivalent is source that can be swapped out for another while leaving all the other circuit current voltage intact. In other words, all the circuit component voltage drop and branch current will be identical to those found in the original configuration. This technique is useful in a number of ways, particularly in that it can help produce more complex circuit to to simplify analysis. The concept of equivalent can be extended beyond just a single source to an entire network. For this, we will examine Thevenin and Norton theorem. Using these theorems, entire circuits utilizing dozens of components can be modeled as a single source with the associated complexity independent. When they couple with the maximum power transfer theorem, this tool will allow us to determine the component value that produce the maximum amount of load power. We will also address the method of analyzing circuits that contain multiple current and or voltage sources that are connected in a non-trivial fashion, not just series voltage source or parallel current sources. This is called the superposition theorem. It can be applied to any circuit or parameter that meet certain requirements, including circuits that have mix of current sources and voltage sources. Superposition can also be used to determine voltage and current when sources are different frequencies. In fact, one way of imagine complex wave shape is to treat it as series of connected sources, each with a unique frequency, phase, and amplitude. Superposition will give us mean to handle a new situation. Superposition is called, this is called the superposition theorem, and this is repeated, sorry. Source conversion. A DC analysis, we noted that real-world sources have practical limits. Voltage source cannot produce infinite current, and current source cannot produce infinite voltage. A simple way of creating a more accurate model for independent source is to include an internal resistance. Internal resistance. For DC voltage source, a resistance is added in series with the source, and for DC current sources, a resistance is added in parallel with the source. While this works well enough for typical DC sources, the AC situation is a little more complicated. This I think, no. These AC current sources are, okay, a DC voltage sources, the resistance is added in series with the source, and the DC current sources, the resistance is added in parallel with the source. Okay. Models for AC sources, just as added as simple resistance to a DC sources to make improved model, we can add a complex impedance to AC sources to do likewise. Once again, it is possible to make even more involved model that will be more accurate, but for most work, this addition will suffice. Generally, there's a wider variation in values for the AC case than the DC cases. We can think AC sources as belonging to one of the two broader categories. First, there are power generators, that is system designed to generate and deliver power for one electrical device. This would include AC main system in a residence or a portable power generator. At the other end, the spectrum are signal sources such as transducer and sensor. These devices are generally low power and are not designed to produce particular high current, quite the opposite of generator. So when we come to AC circuits, most practical application in electrical engineering involve alternating current, voltage, and maybe I have to say thank you. This will be the next lecture. So let's close this one, then starting